Lesson 7.1 is talking about exponential functions, and we're going to explore those specifically in the financial realm of things so that you guys can see how some certain things are calculated exponentially. But the prefix of that should give it away as far as what these functions should look like. All right, exponent. If something's going to have an exponential relationship or an exponential function, it's going to have an exponent in it. Where most of the functions that we're dealing with, at least in Algebra 1, okay, were linear relationships and a constant rate of change. Well, these ones aren't going to be a constant rate of change. It's going to increase exponentially. So, first thing I want you to review, or I'm going to review with you, is powers. Right? When I say powers mathematically, that's the same thing as an exponent. So we're going to cross out the expressions that are not powers. So looking up there, which one of these do not have a power? Cross those out. Those are linear relationships. So like this scenario here, maybe you get paid $16 a month, or you got to pay $16 a month every single month. This relationship here means like maybe it's you're signing up for a membership somewhere. You got to pay $7 straight up, and then you got to pay $6 a month after that. Okay, those are linear relationships because it's consistent. You might start at $7 in the hole, and you got to pay $6 every month, but it's $6 every month. All right, where these ones, okay, that's not that anymore. X cubed, okay, it's x times x times x, not x plus x plus x. So like when you're adding, okay, and that's more of a linear relationship. When we're multiplying, that's going to be more of an exponential relationship from one ordered pair to the next. So with number 2, let's continue that idea. We're just going to circle the exponents. Then on your screen, it would really help if you zoomed in. Yours are going to look a lot better than mine. But if you zoom in, I want you to go ahead and circle all the exponent values. All right, so between the 5 and the 6, which one is the exponent? 5 or 6? Okay, so go ahead and circle that. That is your exponent. And then continue. All of them. So keep going all the way through all of those and circle. All right, circle the powers that are there. So the review is just quite simply just getting you guys to understand, okay, we're interested in these powers, but more specifically as we go through these notes, we're going to learn, okay, well, when we try to relate a situation with a power, how does that, change the relationships between its input and its output? Well, there's 2 possible exponential functions you guys are going to have to be able to tell the difference between, and that's an exponential growth and an exponential decay, because those are both scenarios. I mean, something could be decreasing exponentially just as well as it could be increasing exponentially. So I would change your color on your screen and highlight, or you can just highlight, whatever you want to do. Highlight what it means to be an exponential decay function. Now, what they say is, and here's the general form of an exponential function. So first of all, look at the value of the x and where it's at. So the input of our exponential function is actually in the exponent itself. Okay, and then we have these 2 values underneath of it, b and a. A is the number in the front, b is the base. So if your a is something positive, so if a is greater than 0, and your b is some fraction or decimal that's between 0 and 1, then it's going to be a decay. I would highlight those 3 things some way, some form, so you guys make those connections. And just a second, we're going to talk about what makes an exponential growth and what those functions are going to look like. But again, I would really emphasize this part right there. That's the big one. Your base, all right, which is nice because they use the variable b. Your base has got to be something between 0 and 1. If that's the case, then it's going to be a decay. So let's see if we can practice that skill with number 3. We want to circle the equations that represent an exponential decay. So again, here you have 2 conditions in order for it to be true. the number in the front, okay, has to be positive, and then the base has to be a fraction. So with the first one, I can see my base of my function be between 0 and 1, so that's good. But my a, okay, is a negative 1. All right, there's really a negative 1 in front there, so that would be bad in the sense that my number in front is not greater than 0. Okay, so that's not a decay. But the next one, where this is, because again, the number in the front is something positive. Right? That's the two things you're checking every time. Is the number in front positive? Yes. Is the base between 0 and 1? Yes. So circle it. All right, so those two questions every time. Is the number in front positive? And is your base between 0 and 1? So with the next one here, is the number in front positive? Or better question, what is that number that is in front of this parentheses right here? It's not actually shown, but what number could I put right there? A 1. So to answer this question, is the number in front positive? Well, if that's a positive 1, then yes, it is. So yes, that's positive, because this one here was a negative 1. That's why we said it wasn't. So yes, this is a positive 1. Is this base a number that's between 0 and 1? Okay, so let's circle it, because 3/4 is 0.75, so that's between 0 and 1. All right, next one over. Again, the number in front is a positive 1, so we're good there. But what about my base? 7/5, is that between 0 and 1? 7/5 is the same thing as 1 and 2/5. So that's actually a number that's larger than 1. Just because it's a fraction doesn't mean that it's between 0 and 1. Okay? Right. So your fractions in which the denominators are larger means that it would be something between 0 and 1. But this is improper, so that's not less than 1. So that's not a decay. Okay, moving forward, you can see this base here, 1.05. That's larger than 1. So that's not good. You can circle the one below that one. That one's okay. They're using the number in front as a variable now. All right, so that as long as that n sub 0 is something positive, then this is an exponential decay because, again, my base is 0.5. That's between 0 and 1. Okay, what about this next one? Is that a decay? It is so small. Yes, it's larger than 1, so that's not a decay. All right, what about the last one? Yes, it is. Again, the 28 is like the A. So again, that has to be something positive. And this has to be something between 0 and 1, and that fits the conditions. And that's the two conditions you have to ask yourself every single time. Okay, for those that just came in, two big conditions for exponential decay. The number in the front has to be something positive. And your base has to be between 0 and 1. So you want to highlight those ideas right there. So let's see if you guys can. There's not one correct answer to these problems in number 4. It's just trying to understand the concepts that will make them true. So write the numbers to make each equation represent an exponential decay. So the first one, the 3 in the front is good because it's positive. Okay, so what number can I put in the space there? Logan says 1/4, and anything that's less than 1. So I can say 0.4, 0.3, 0.2. You can do a fraction, 1/3, 1/4, 1/5, as long as it's proper. You don't want to do an improper fraction, because then you're back to that scenario. All right, what about the next one? So again, the 0.02 is positive, so that's good. That meets that condition. But what can I put in the box on the top if I have a fraction? My bottom's a 2. I'm kind of forced to make that a 1. All right, I can't make it a 3, because again, that would be improper, and it'd be back to this idea. All right, because 3/2 would be something larger than 1. All right, so with that case, next one, what can I put on the bottom? Again, it's got to be, if the top number is a 3, can I put a 2 on the bottom? Can I put a 2 on the bottom? Because that would make it 1.5. All right, it's got to be something less than 1. So if this is a 3, then I can make this a 4. Can I make it a 5? 6, 7? So anything larger than 4, right? And then that'll make the base between 0 and 1. So the next problem is going to be talking about an exponential growth. And I want you to add those two conditions right here before we're going to give ourselves a visual as far as what these exponential functions look like. But I want you to make note of the two conditions that we're looking for when it comes to looking for a growth. So first of all, right, so our general form of an exponential function is a times b to the power of x. And I'm saying my a has to be something positive, and my b, okay, or my base of my exponential has to be something larger than 1. Then that will be I'll put this in, we want to put this in quotes or something. That will be a growth. Now, this problem here is an exponential growth because, again, the number in front is another positive 1 because it's not there, so there is a positive 1 there. And my base is a positive 4, so therefore I know this is a growth model. All right, now let's go ahead and complete this t-chart. So they give me some values of x, and I'm going to plug that in for my x. So that goes in for the exponent. So the first one would be 4 to the power of negative 3. And this is some of the things you've been doing on Carnegie. If you have a negative exponent, we can put that on the bottom positive, which then is 4 times 4 times 4, which is 1 over 64. So if you just want to write 1 over 64, you can. Okay, but that's a property of exponents that you have been rehearsing in Carnegie. 4 to the negative 2 is the same thing as 1 over 4 squared, which is 1/16. Okay, so 1/16. 4 to the negative 1 is 1/4. Here's a property that was also tested on Carnegie. What's anything to the power of 0? 1, yes. So 4 to the power of 0 would equal 1. 4 to the power of 1 is 4, and 4 squared is 16. All your exponential growths will have this relationship, and as your x's get further and further negative, if you notice, it's always going to be something positive. It's going to get closer and closer to 0 because you're taking 1 divided by something even larger every single time. And then as your x's increase, so do your outputs, and they increase very quickly. All right, it's not increasing at a constant rate. All right, instead, it's increasing by a product. So if it was a linear relationship, it would be you would add 4 each time. Well, exponential relationships, the outputs increase by some product, or in this case, a product of 4 each time. Now, as far as graphing this goes, I would only graph 2 ordered pairs. These ones here are really hard to graph, or basically just say it's just going to get closer and closer to 0. But this order pair 0, 1 is an easy order pair to graph, and then the next one right after that, 1, 4, is another easy order pair to graph. Next one after that, you're going to be way off the chart. 2/16 is going to be way up here. So if it's a growth, something I want you to note in the visual of this is that it never goes below the x-axis. So in other words, your range So we're talking about the range of this function for all exponentials. That's going to be greater than 0 every time. And that's also true for decays. Decays will look like this. Just FYI. All right, so if it's a decay, it's going to go like that. So growths go up from left to right, and decays will go down from left to right. I'm going to erase the decay. I just kind of wanted to mention that just for your information, since you're working with both. But your notes give you a good example as far as what a growth looks like. And again, that's increasing from left to right. Again, I would highlight this. There's a highlight button on the draw feature, or you can underline it. But the two things that you're looking at is really, it comes down to this B, all right, which is the base. If you notice, the A must always be positive. All right, that condition is true for both. But if your B is greater than 1, then that's a growth. So make those two connective pieces there. And if it's between 0 and 1, it's a decay. All right. Yeah. I want you to make those connections because, again, it comes down to this base. That's the only difference in the two conditions. So if this base is something larger than 1, we call this a growth. And if this base here is between 0 and 1, we call it a decay. So let's use that and see if we can define those for number 7. So y equals 3 times 5 to the x. Is that a growth or a decay? Okay, so this one's a growth because, again, my base is larger than 1. My a is positive. All right, so now this next one. Okay, my a is 1/2, because that's the number in front, and my base is 7. So the only thing I care about my a is whether it's positive. The fact that that's a fraction has nothing to do with whether it's a growth or a decay. It's just the fact that it's positive value. So this is positive. Again, my base is 7. So is that a growth or a decay? Good. Okay, so again, my number in front is positive. My base is 1/3. So this base is between 0 and 1. So that is which one? Decay. And the same thing for the last one. Because again, my base is between 0 and 1. It's all about the base when you're trying to decide whether it's growth or a decay. All right, let's get to, just do this one more time, and it's going to take you through all of those steps again. All right, so we have a function 3 times 4 to the x. Okay, so a is the number in front, and b is the base. So in this scenario, what number is a? Is it the 3 or the 4? Again, a is the number. It's not that hard. I should have an abundance of answers, not just 1 or 2. A is the number in the front, and b is the base. So which one is the a? 3. And the base is the 4. That's the number on the bottom. Okay. So if that's true, all right, the value of b, is it between 0 and 1 or greater than 1? It's greater than 1. Is that a growth or a decay? It's a growth because it's larger than 1. Okay, and then here is a new topic, and you can put this in a different color if you want to, but the a also tells us something else. It tells us the y-intercept. So your y-intercept is what a is. Okay, so whatever number is in the front is also the y-intercept, and the reason being is, all right, if I make my t-chart, okay, and I put 0 in, which is where the y-intercept, the x value is always 0. If I plug that in, what is 4 to the power of 0? 4 to the power of 0 is 1. Anything to the power of 0 is 1. So 3 times 1 would just be a 3. Okay? So it's basically, that's why it's always the number in the front, because this value will always be 1, and 1 times whatever will just be whatever. Okay? So y equals a b to the x for all scenarios. If I plug 0 in, you're going to have a b to the 0, which then is a times 1, which then is just a. Okay? All right, 2 more problems and we're going to be done for today. So here we go. So here's some situations that you guys will use this general exponential function to model and find whether it's a growth or a decay. You'll be able to figure out the total amount, okay, over a certain period of time. So t could be the number of years, it could be the number of months, it could be whatever, okay, but your rate, so whether it's increasing or decreasing at a certain percentage, okay, you're going to do 1 plus that. And then your A is your beginning amount. So the most common, we got a couple scenarios down here, but the most common scenario that we use this formula for is the money situation. And I was telling you in the beginning of the period. But again, initial amount is A. T is the number how long you're going to do it for. And if we do that exponential relationship, you get the total amount that you have left over. So for example, all we got to do is connect these. But let's say you buy 50 mice. Okay, well, the fact that you're buying 50 mice, that's an initial value, so that has to be the number in front. So wherever you're starting is always a number in the front. And then it increases by 15%. The population of mice increases by 15% each month. So I'm going to have 1.15 because my rate is 15%, which is 0.15 as a decimal. Okay? 15% is per 100. And anytime you divide something by 100, it's 0.15. So this inside is 1 plus 0.15, which is where you get your 1.15, in other words.
Okay, what does that say?
Percent is the same thing as per 100, which I'm just trying to show you when you're trying to convert percentages to decimals, all you're doing is moving the decimal point 2 places to the left. All right, so the next one, you buy a pound of dog food. So that would be the bottom one there. Okay, so it starts with a pound of dog food, but then it eats a quarter each time. So that's a decay because it's going to keep eating a quarter of what it has every single time. So that's why this is 0.75, because again, it'd be 1 minus 0.25. So it's going down 25%. The dog eats 25% each time, which means that it's 75% of its original value every time. All right, you get paid. Here's your money examples that you guys are probably more interested in as far as what you use more commonly. But you have a job that pays you $8 an hour. So that's the initial amount. That's where you're starting at. Well, if your employer says your salary is going to increase 5%, okay, every year, that's an increase. So that's going to be represented by 1.05 because, again, it's 1 plus 0.05 because 5% is 0.05 over a certain period of time. Another one, savings accounts. All right, this is true for a lot of companies. So it depends on some savings accounts, depending on the bank, they'll charge you if you don't keep a certain amount in that savings account. So here's a scenario where they're going to, if it's under $1,000, they're going to charge you 2% just because you don't keep that certain amount in there. So in this case, you have a person that only has $300 in their savings account. Okay, well that means they're going to lose 2% each time. So 1 minus 0.2%. But you're going to start at $300, but that's going to go down exponentially every single time because you're going to lose 2% each month. Let's do another money example, and we'll close class with this, and we'll finish it tomorrow. Hopefully you guys realize this will apply to stocks, investments, certificates of deposits that you guys want to invest in. But you can make money without doing anything besides just leaving it in that account. It'll constantly accrue interest and accrue money depending on which one you use. Let's go through this scenario. So let's say we have $500. We're going to put in a savings account. The bank tells you you're going to earn 3.5% annual interest. So annual means what? Yearly. Good. So how much will be in your account after 5 years? So you're just going to leave it in there for 5 years and see how much you have. So here we go. Is this a growth situation or is this a decay situation? It's a growth. All right, so it's going to be increasing because you're going to earn interest at 3.5%. Okay? So what is the initial amount that we're investing? How much money are we going to put in there initially? How much money are we going to put in the savings account? We're putting $500 in there, so that is my A. All right. What is the rate? 3.5%. So let's fill those blanks in. So 500 must be the A. That's always the number in front when you're using your formula. And then this needs to be the decimal value of 3.5%. So what is a decimal? Because this is per 100. So what is a decimal equivalent of 3.5%? If you move it 2 places to the left, it's going to be what? 0.035. So here's our function. That will tell us how much money we have in our account. If we take 1 plus 0.035 is 1.035. All right, and then T is the number of years. Now, how long are we going to leave this in? We're going to leave it in there for 5 years. So this will tell me my amount. Again, you didn't do anything. You just left it in the savings account and then just let it accrue interest. But when you calculate these, make sure you do order of operations first. So make sure you take it to the power of 5 first, and then times it by 500 second. I'm getting $593.84. All right, we'll finish the rest tomorrow.